Hey, welcome to another video by Professor Gilmet. And today what I'd like to talk about is what is a p-value, okay? A lot of misconceptions about what a p-value is and is not, and why we use certain language. So I want to address that today. So let's suppose you had a research question, right? And you collected a random sample, you conducted a hypothesis test, did all the calculations, right? Now you're staring at a probability. But a probability of what? Like, why is that p-value there? Well, a p-value is the probability that if the null hypothesis is true, then we have this probability of getting a sample or one more extreme. Okay, so it could be greater than or less than, depending on what kind of hypothesis test you're doing. Now, this is kind of mathy. So what I want to do is use a real-world example to help us. All right. So, you know, Arrow is my favorite, and I have kind of a theme going on the channel recently. So this video is no different. Team Arrow fights against crime in Star City. They have averaged stopping 2 crimes a night for the past month. Oliver and company get back to the lair, and Felicity says, "You have kicked butt 4 times a night this week." And so Oliver is thinking, wow, I wonder if something is happening, you know, something big planned by the villain. Is it possible something is happening, or is it just the high side of a normal week? You know, do we have strong evidence here? So we're going to conduct a hypothesis test, testing this claim of unusual for the week. Assuming that this week means assuming that this was a normal week is the null hypothesis. Okay? And so we would say that mu is equal to 2. No change, still 2 times a week as it's been over the past month. But an unusually busy week would be our alternative hypothesis that something is up, and that would mean that it's actually greater than 2. Okay? So I do the calculations to get a p-value. And it's equal to 0.0998. Just editorial note, I did do a random simulation. Actually, I did a bunch of random simulations and picked one simulation for this. So what does this mean? Okay, if this was a normal week, then 9.98% of weeks will have an average of 4 or more crimes stopped. So if this was a normal week of, you know, the average is still 2, then about 10% of the time we expect a week like we had just simply due to random variation. Okay? So in fact, our week is actually represented by the white area on the sampling distribution below. Okay? So look, here is our sample and the greater than. Okay? And there's our probability of about 10%. You see, there's a lot of red, representing weeks that are 4 or more crimes stopped on average. So it does seem like this is just a random variation and not unlikely. And this is because we got a value we would expect just from normal week-to-week changes, even if the average overall is still 2. Because we're never going to have a crime-fighting week that is the same as another. Every week, every night is going to be different. So we're inclined to believe that the average is still 2 crimes stopped per night, and that nothing really nefarious is afoot. Okay? But what is the logic behind the p-value? Which decision am I going to make about the null hypothesis? If this was a normal week, that the average is still 2 crimes stopped per night, then 9.24% of weeks will have an average of 4 or more crimes stopped. The week was fairly normal, so we are not able to say this was not a normal week. Okay? Now, I apologize for all the double negatives, but this is the way stats are conveyed, and for a really good reason. It turns out that logic and mathematical arguments are at the root of the language here. These simple if-then statements that I have been using can be generalized in the following way. let P and Q be statements that are either true or false. Okay? The dog is brown. That's either true or false. Arrow is a superhero. That is true or false. Okay? Then we have to follow logic. All right? So what are the logical rules? If P then Q, if that statement is true, okay, that statement is true. If P then Q is a statement that is true when P and Q are both true and both false. Okay? And so the logic of the argument is therefore, if P then Q, if that statement is true and Q is true, the conclusion is, well, we don't actually know. P could be either true or false. Okay? And this is why we don't accept but fail to reject. Right? Because we assume that if this week was normal, then 9.24% of weeks will have an average of 4 crimes or more. We're assuming that that's true. And the 9.24% of weeks that have an average of 4 or more crimes stopped actually seems pretty reasonable. It seems true. Then our conclusion is this was a normal week. Probably. Okay, but we can't be sure because the logic says it could be either. But it seems sensible to say that this was probably a normal week. Fail to reject. And that's why we do the fail to reject. Okay? Now, what about a different situation? What about when we get something even less likely? So let us change that Arrow situation just slightly. Team Arrow fights against crime in Star City. They have averaged stopping 2 crimes a night for the past month. Oliver and company get back to the lair and Felicity says, "You've kicked butt 5 times a night this week." Oliver's thinking, wow, I wonder if something big is going to happen. Right? Is it possible that something big is going to happen, or is it just a busy week? So again, we would conduct a hypothesis test for this claim to see if it's unusual. Assuming that this was a normal week means the null hypothesis is again that mu is still equal to 2. The average overall for fighting is still 2 crimes stopped a night. But an unusual week, a week where I would reject that and say the average is now different, I would say is greater than 2. Now, when we do the calculations on the simulated samples that I did, I got a p-value equal to 0.0037. Now, this is a whole lot smaller than before, but what does it mean? Okay, so about 3 weeks out of 1,000, we expect a week like we just had simply due to random variation. In fact, our week is represented by the white area on the sampling distribution below. The red area, sorry. Look, it's that little teeny sliver right there. Not a lot of red this time. I mean, can you even see it on the screen right there, that little sliver? So what is the logic now? Well, it's actually the same logic, but one of the statements is now false. If this was a normal week and the average is still 2 crimes stopped per night, then 0.38% of weeks will have an average of 5 or more crimes stopped. This very small bit right here. This week was not fairly normal. Only about 3 weeks in 1,000 should be like this. So this is not really very reasonable. And so we are able to say very strongly that this was not a normal week. How can we be so sure this time? Well, in fact, we could have made an error, okay, but logically the argument is still very strong. It is set up this way. If P then Q as a statement is true and Q is false, the conclusion is P actually has to be false. And this is why we use the language of reject here. because we are saying that this is false. Now, yes, we could have made an error, but the logic says we reject. And the reason for this is the well-known argument of the contrapositive. And simply put, or as simply as I hope, is if P then Q as a statement is true, and not Q is true, then the conclusion is not P is true. Now understand, if not Q is true, then Q is false. And if not P is true, then P is false. It's the opposite value. Okay? So, interesting. Because if we assume that if this week was normal, then 0.38% of weeks will have an average of 5 or more crimes stopped is true, right? The essence of our p-value, the definition, and 0.38% of weeks will have an average of 5 or more crimes stopped seems unreasonable, but still happened, Q is false, then our conclusion is this was not a normal week and mu is not 2 anymore. It's actually greater than 2, making P false. And so Team Arrow should get ready because it looks like something big might be getting ready to happen. Okay? Now, I want to say a couple of things in closing. One, this is not an easy thing to wrap your head around. It involved formal logic and probabilistic language. It took me a couple of months of thinking about it and talking about it to really understand it. The catalyst for that was Cohen's "The Earth is Round, P is less than 0.01. For a higher level explanation of the logic and why effect sizes and the power test is important, please read this article. You know, it was really enlightening for me, especially if you understand logic. I'm not sure you need to completely understand everything to benefit from this video. You don't really need to understand everything that I did. If you understand things a little bit better, great. Here's the main point. As a sample becomes more and more unlikely, the probability of them happening goes down. Way, way down. And at some point, we say the probability of an event is so unlikely that the fact that it happens makes us question our assumptions, our null hypothesis. And this is why we reject. So for everyone about to say I haven't constructed the logic correctly, I would refer you to one. I really wanted to make this as easy as possible to understand without saying anything incorrect. And I actually think that that's true. I've gone over this a couple of times. I think everything is true, even though, yes, the logic is simplified. Again, if you want a really deep, comprehensive look at the logic of a p-value, please see Cohen. And if you did understand better, that is awesome, and that makes me happy, and that's why I do these videos. So if you did understand better, please, subscribe, like the video, leave me a comment, and I will see you again soon.